Simple harmonic motion, periodic motions, oscillatory motions, simple harmonic motions SHM. Tiny motions which repeats itself after regular interval of time period is called periodic motions or harmonic motions. Example: motions of planets around the sun, motions of pendulum of wall clocks. Oscillatory motions: the motions of body is said to be oscillatory or vibratory motions if it moves back and forth to and fro about a fixed point after a regular interval of time. The fixed point about which the body oscillates is called mean positions or equilibrium positions. Example: vibrations of wire of sitar and oscillations of mass suspended from a spring. Simple harmonic motions SHM. Simple harmonic motions is the simplest form of vibratory or oscillatory motions in which restoring force is directly proportional to distance from mean. Some basic terms in SHM: mean positions, the point at which the restoring force on the particles is zero and potential energy is minimum, is known as its mean positions. Restoring force, the force acting on the particles which tends to bring the particles toward its mean positions, is known as restoring force. Restoring force always acts in direction opposite to that of displacement. Displacement is measured from the mean positions. Amplitude. Amplitude, the maximum positive or negative value of displacement of particle from mean positions is defined as amplitude. Time period, the minimum time after which the particle keeps on repeating its motions is known as the time period. The smallest time taken to complete one oscillations or vibrations is also defined as time period. It is given by T is equal to 2 pi upon omega or is equal to 1 upon n, where omega is angular frequency and n is frequency. Frequency n or f, number of oscillations per second, is defined as frequency. The phase of a vibrating particle at any instant is the state of the vibrating particles regarding its displacement and directions of vibrations at that particular instant. In the equations, x is equal to a sin omega t plus phi in bracket omega t plus phi is the phase of the particles. The phase angle at time t is equal to 0 is known as initial phase or epoch. The difference of total phase angle of two particles executing SHM with respect to the mean positions is known as phase difference. Two vibrating particles are said to be in opposite phase if the phase difference between them is in odd multiples of pi, that is del phi is equal to in bracket 2n plus 1. pi, where n is equal to 0, 2, 3 and so on. Angular frequency omega, rate of change of phase angle of a particle with respect to time is defined as its angular frequency. Omega is equal to under root k upon m. Linear SHM, f directly proportions minus x. F is equal to m del square x upon del t square is equal to minus kx is equal to minus m omega square x, where omega is equal to under root k upon m. For angular SHM, torque alpha minus theta, torque is equal to 1 d square theta upon dt square is equal to I alpha is equal to minus k theta is equal to minus m omega square theta, where omega is equal to under root k upon m. Displacement x is equal to a sin omega t plus phi. Angular displacement theta is equal to theta naught sin omega t plus phi. Velocity v is equal to del x upon del t is equal to a omega cos in bracket omega t plus phi is equal to omega under root a square minus x square. Angular velocity del theta upon del t is equal to theta naught omega cos in bracket omega t plus phi. Accelerations a is equal to d square x upon dt square is equal to minus a omega square sin omega t plus phi is equal to minus omega square x. Kinetic energy k is equal to 1 upon 2 mv square is equal to 1 upon 2 m omega square a square cos square in bracket omega t plus phi. Average energy in SHM, the time average of potential energy and kinetic energy over one cycle is kt is equal to 1 upon 4 a k square. Potential energy in T is equal to 1 upon 4 k square. The positions average of potential energy kinetic energy between x is equal to minus a to x is equal to a. Kx is equal to 1 upon 3 k square. Kinetic energy is equal to kinetic energy x is equal to 1 upon 3 k square. Potential energy x is equal to u naught plus 1 upon 6 k square. Total energy x is equal to 1 upon 2 k square plus u naught. Angular accelerations del square theta upon del t square is equal to minus theta naught omega square sin in bracket omega t plus phi is equal to minus omega square theta. Kinetic energy k is equal to 1 upon 2 mv square is equal to 1 upon 2 m omega square a square cos square omega t plus phi. Potential energy U is equal to 1 upon 2 kx square is equal to 1 upon 2 m omega square a square sin square omega t plus phi. A spring block system t is equal to 2 pi under root small m upon k. T is equal to 2 pi under root small m upon k m1 m2. T is equal to 2 pi under root mu upon k, where u is equal to reduced mass is equal to m1 m2 upon m1 plus m2. Series combinations of a spring. T is equal to 2 pi under root m upon k effect, where 1 upon k effect is equal to 1 upon k1 plus 1 upon k2 or 1 plus 1 upon k3. Total kinetic energy E is equal to k plus u is equal to 1 upon 2 m omega square a square constant. T 1 upon 2 k square displacement time 1 upon 2 k square t. Parallel combinations of a spring. T is equal to 2 pi under root m k effect. Time period of simple pendulum. Time period t is equal to 2 pi under root l upon g. Second pendulum. Time period is equal to 2 seconds. Length is equal to 1 meter on Earth's surface. In total kinetic energy of a particle in SHM is same at all instant and at all displacement. Total energy depends upon mass, amplitude and frequency of vibrations of the particles executing SHM. Time period of physical pendulum. T is equal to 2 pi under root I upon mgl is equal to 2 pi under root k square upon L plus L upon G, where I center of mass is equal to mk square. Time period of torsional pendulum. T is equal to 2 pi under root I upon k, where k torsional constant of wire, I moment of inertia of the body about the vertical axis. Time period of conical pendulum. T is equal to 2 pi under root L cos theta upon G is equal to 2 pi under root Hg. In accelerating cage, accelerations increase, G effect is equal to G plus A. Acceleration decrease, G effect is equal to T is equal to 2 pi under root L upon G plus A. Acceleration decrease, G effect is equal to G minus A. T is equal to 2 pi under root L upon G minus A. Accelerations constant, G effect under root G square plus a square. T is equal to 2 pi under root L upon g square plus a square in bracket 1 upon 2 bracket to power 1 upon 2. Important point: SHM is the projections of uniform circular motions along one of the diameters of the circle. The periodic time of a hard spring is less as compared to that of the soft spring because the spring constant is large for the hand spring. For a system executing SHM, mechanical energy remains constant. Maximum kinetic energy of a particle in SHM may be greater than mechanical energy as potential energy of system may be negative. The frequency of oscillations of potential energy and kinetic energy is twice as that of the displacement or velocity or accelerations of particle executing SHM. Executing